Hi, everybody. Welcome to National Hydrologic Warning Council's April webinar. We'll get started here in just a minute. I'm going to allow another minute for some more attendees to log on. Okay, I'm starting to see some more people get online, so let's get started with our webinar. Hello, welcome to National Hydrologic Warning Council's April 2022 webinar. I'm Matt Riddlebarger. I'm the webinar facilitator. Today, we have Mark Hubbard from Campbell Scientific, and he'll be giving a presentation on radio antennas and testing. If you have any questions during Mark's presentation, please use the questions feature, and I'll read out your question to Mark. Without further ado, I'm going to pass it over to Mark.
Okay. Very good. Well, thank you, Matt, for inviting us to be able to talk today. I just want to double check, are you all able to see full screen of the presentation at this time?
Not yet, Mark. Yes, that's perfect.
Okay, we'll try that again. Okay, well, again, thank you for everyone who's attending. Appreciate your time being here today. My focus today is talking about radio antennas that are typically used in warning systems. It's the general discussion about issues and issues that come up as far as installing antennas, maybe some good antennas to use, some antennas that have been found to fail in the field and might want to be avoided, and ways of testing antennas and antenna cables to know if the antennas are performing as best as they can, or if you have any kind of problems that come up with them. Again, I'm Mark Hubbard with Campbell Scientific, and feel free to shoot any questions you have during the presentation. I'll be glad to answer them as much in real time as we can. And always love getting your feedback as we go along. One second. I apologize, so we can pause here for just 1 minute. We need to fix whatever is going on. Okay, I apologize for that. Within these warning systems, as you all know, there's a real need for reliable communications. Warning systems need to be robust and reliable and need reliable communications 24/7. And of course, these systems need to operate in all kinds of weather conditions, all very difficult as far as electronics to operate in and as far as instrumentation as well. The field installations need to be designed to support long-term uninterrupted use. The equipment needs many times is placed in limited access locations, so difficult to get back to if there is a problem. And so quality of product and quality of materials used in the installation are key. The antenna systems themselves need to be maintained. Many times, once the systems go in, kind of the antennas are forgotten, and it's the instrumentation and all the other items within the equipment that are key and of high priority. But the antenna system, along with the radio system, are very important in order to get full performance out of the site and have reliable updates from each site when needed. These kinds of systems, of course, need to be installed right the first time. Very difficult to get back to some of these sites. They may be only accessed by helicopter certain times of the year. They may be on top of very snowy peaks where you can takes quite an effort and months, if not years, planning to get there and to be able to do installations. So once you do an installation, you want to be able to test at that time to make sure that the antenna portions of the system are working correctly, and you can fix any problems that are detected. Again, very costly to go back to a site and have to fix an antenna problem or a cabling problem that could have been caught in the beginning, in the initial installation, if you had the right test tools to be able to do that. Some of the common wireless technologies that are used currently for a lot of these systems, licensed VHF, UHF radio, it's been used quite a bit for these systems. It has very quick response, very high reliability. It does basically tend to be for lower data rates, but a lot of this data, although it's time sensitive, there isn't huge amounts of data that need to be passed as far as warning indicators or levels overflowing or what have you. Unlicensed ISM band 900 megahertz, 204 gigahertz is also used. Has a reduced range over VHF, UHF licensed radio. Still has quick response and can handle a bit higher data rates than the VHF, UHF narrowband products typically can. And the cellular service is becoming more and more popular as stability in the networks increases. Of course, you have regional coverage, not coverage everywhere, but coverage is getting better and better. Still can get pretty quick response as far as alarms or any kind of alerts that need to be done. And of course, you can support medium and very high data rates. And that is just continuing to grow as 5G gets put into place and the next technologies that move forward with that. And then there are satellite links available. They're getting better over time. Basically, being able to have quicker response. There's still slower responses typically than most of the other communication mediums, but these systems are getting better and better, and over time we'll see quicker responses. Some systems can be down as low as about 20 seconds, which in some cases is okay, some cases is not. But again, that's still evolving, and I think we'll see some real growth there over time. Why antennas matter? Typically, antennas can be some of the most exposed elements in the equipment that's set up. It many times is the highest instrument or item on a tower or a mast. And if it goes down, if it fails, your communications fails, and then the site is basically useless. Sensors, although we don't want them to fail, if you lose one or two sensors, you can still probably get a reasonable amount of data and know somewhat what's going on. But if the antenna goes down, just like if the radio goes down, you've lost your communications. So the antennas are exposed, and they're vulnerable as far as operation. So installation is critical, that it's installations are done in a robust way, and that they're designed and installed to stay in place for a long period of time. I apologize. I'm continuing to have problems with scrolling through these slides. Okay, again, I apologize. So the remainder of this presentation is going to include different topics having to do with antennas and a little bit on radio systems, as far as some tips for doing installations, as well as, again, some gotchas that we've probably all run through, and just sort of highlighting some of those items here. Matt, I'm going to have to apologize to you. I do not know what is happening here.
Yeah, sure. I can put up just a slide while you're getting your slides figured out.
Go ahead, please.
Okay. Just to let everybody know, I know it says it here on the slide, but I didn't mention it. The recording of this webinar and previous webinars that we've done will be uploaded to the National Hydrologic Warning Council's YouTube page.
Matt, I think we're back up and running.
Okay. All right, I'm gonna switch it over to you.
Okay. Again, we'll walk through each of these different items and kind of talk about these in a little bit more detail. We'll go from there. Again, I apologize for the slide problems that I'm fighting here. Matt, for some reason it locks up when I start sharing my screen. Sam has offered to show the slides and then I can talk to them. Let me give me another minute. Let me get these slides over to Sam and get it set up that way, if that's all right.
Yeah, okay, that sounds good.
Okay, thank you. And again, to everyone, I really apologize for this mishap here.
Mark, do you know if Sam's ready yet?
He he's just gotten the slides. He's getting that set up.
Okay.
Sam is still waiting to receive it.
Okay, thanks. Okay, he says he's ready. I'm going to go ahead and make him the presenter now.
Okay.
Sam, you're unmuted, just FYI.
Okay, should be able to see my screen now.
Yeah, we see the notes view though.
Okay. Then should see the other view now.
Yes, presentation view, perfect.
And Mark, you just let me know when you want me to progress, bud.
That sounds great. Yeah, you can go to the list of topics. Perfect. Thank you for everyone for hanging in there. We'll continue now and hopefully not have any more difficulty. Again, we'll walk through each of these items and talk a bit more in detail about each of these. Next slide. Basic radio system components. You're all very aware. Includes radio, some sort of power source to run the radio, and then highly recommended using lightning arresters on the antenna cables, and also using sometimes in some cases cable ground straps as well on the coaxial cable, depending on how long the coaxial cable run is feeding the antenna and how high off the ground the antenna is. Some of the issues we'll be talking about today have to do with measuring signals feeding from the transmitter to the antenna, and then in some cases signals that are reflected back from the antenna back to the radio transmitter. Next slide is fine. Transmit power. Well, look at the various specifications on radios, and we all have this tendency to say, wow, that has a higher transmit power. That's a great thing. We'll go with that because I should be able to transmit farther. But there are some caveats with that, which can be a real issue. Transmit power is overrated. You can increase transmit power and get some additional range, but it's at a cost. It's at a cost of more expensive transmitters that can handle the higher power. It's also at a cost in that the DC power or AC power needed to feed the transmitter increases quite drastically as you go up in transmit power. And you don't get a lot of improvement in range typically just by increasing transmit power. In free space or perfect line of sight conditions, you have to quadruple the transmit power to get twice the range, twice the communications range. And that's only in kind of an ideal setting. If you're in a non-line of sight condition, you might have to do 6 times, 8 times the transmit output power in order to get twice the range in the system. A much better way and a more cost-effective way to try to get more range in the communication system is to increase antenna gain. Leave the transmit power where it's at, 1, 2 watts, 5 watts, more or less. But either buy more expensive antennas that have higher gain, and or put the antennas higher off the ground if possible. Going to a small tower or what have you can make a huge difference. Going from 10 feet off the ground to 30 feet off the ground can make a much bigger difference than increasing transmit power, and with the costs, the power costs, and the expense of using higher transmit power. So with antennas, you can solve a multitude of problems. Plus, with increasing antenna gain, it helps both the transmit signal being sent out from the site. It also helps the site to receive signals from other locations, since the gain of the antenna can be used equally in both transmitting and receiving signals. So there's some real benefits in, instead of increasing power, transmit power, improving your antenna performance one way or the other. Next slide. So I'm going to go through some common antennas that are used in a variety of these types of weather stations and flood warning stations. Typically, there's either some sort of directional antenna. They're typically called a Yagi antenna. And they typically have a horizontal boom and then a number of perpendicular elements to that boom. The number of elements typically indicates the gain of the antenna. The more the elements, the more the gain, the tighter the beam width that antenna is radiating. It's the direct trade as far as the bandwidth and the beam width of the antenna versus what the gain of the antenna is. The other types of antennas that are used typically are vertical, what are called collinear antennas. They're basically radiating elements stacked one on top of another. The taller the antenna normally indicates more gain in the antenna based on having more and more of these elements stacked basically linearly, vertically in the antenna. So these are two very common antennas that are used, and there are many variations of these antennas. Next slide. There are, however, many antennas out there that you should avoid using. And you may have been bit by some of these antennas in the past. We certainly have, and kind of learned some lessons in the process. Some of the directional, these Yagi antennas, use a matching circuit, or basically a cable to antenna interface that is mechanically not very sound. Typically these antennas are referred to as having a gamma match. Gamma was basically the inventor of this type of antenna and this type of matching of the coaxial cable signal to the antenna. But mechanically, these are very prone to corrosion, and they're very prone to loosening over time, and basically making the antenna useless. They're typically set screws on some of the sliding arms that are on there that are very difficult to set permanently. And again, you get corrosion around the elements and the shorting stub that you see there in the center picture on the bottom. And it just makes for a low reliability antenna. If you have some of these in your systems, over time, you might want to replace them with non-gamma match type Yagi antennas, just to improve reliability of the antennas themselves. Next slide. Another basically antennas that are used in the field but are really not meant to be used properly in that environment are whip antennas that either have ground plane using some sort of wire ground planes, or have some sort of ground plane that maybe they're just using the top of a metal enclosure as the ground plane for the antenna. These are typically poor performers in the field over time. Typically the ground plane size that's needed for these whip antennas is normally much larger than what is provided to the antenna. The ground plane should be a radius of the quarter wavelength of the operating frequency of the antenna. We'll get into some of those lengths a little bit later. But these antennas have been used quite a bit in the past and do not perform well. Plus, without having a proper ground plane on these antennas, their radiation patterns are not consistent and can vary quite a bit. Even though they're touted to be omnidirectional antennas, their radiation patterns are very much not that way in many cases. So find these kinds of antennas you want to avoid putting into the field. The upper antennas there, they're great if you want to put them on a vehicle right in the middle of the roof, where you're using the roof of a vehicle as the ground plane, and it's typically more than a quarter wavelength radius. But if you put these on a small NEMA box, you're not providing the kind of ground plane that they need to really operate correctly. Next slide. Antenna cable feed lines are also very important. as far as what is selected and what is used. There are coaxial cables that are referred to as contaminating cables that over time the interconductors contaminate by basically UV radiation, and as those inner dielectrics contaminate, the attenuation of the cable just starts to go up and up and up and up and up. And a cable that you might have just a couple dB of loss in, when you first install it, after 10 years might have 30 dB or 40 dB of loss in it, and it's a very gradual change and sometimes not easily found. The Corps of Engineers in the Sierras just went through a process about 2 years ago, a little longer ago than that, of replacing all of the coaxial cable that was put in some 30 to 40 years ago because of contaminating coax. So we highly recommend certain brands of coax that are made to be non-contaminating. Plus, we recommend any antenna cables that are placed outside of an enclosure going to an antenna. It really should be double shielded cable. Double shielded cable to really help mitigate any RF crosstalk or any interference induced into other radio systems that might be co-located with this equipment, whether it's VHF versus Wi-Fi or VHF versus an ISM band radio or a satellite radio, as well as you may have RF crosstalk from the coaxial cable getting into sensor cables and other instruments that may be on the tower or on the mast that's co-located with the other equipment. So we highly recommend using double shielded coaxial cable external to the enclosures in both the LMR series that's listed there, as well as the RG, the standard military RG series that are listed there are all good cables that can be used. All non-contaminating coaxial cables and all double shielded. A good antenna, an antenna, if designed properly, wants to radiate all of the energy that the transmitter is feeding to it, as long as the antenna is tuned to the frequency that the transmitter is transmitting on. And conversely, whatever frequency the receiver is receiving on, if the antenna is tuned properly to the frequency that the receiver is operating on, the antenna absorbs all of the energy it can and feeds it down the antenna cable to the receiver. If the antenna is poorly matched between the transmitter, or let's say the radio and the antenna, you're going to get reduced performance, and it is going to affect overall the performance of how well the site can receive and how well the site can transmit. A good measure of the quality of the matching between the radio and the antenna can be detected and measured using what's called forward power detection and reflected power detection, or measuring both of those values. A good antenna will take all of the energy, all of the forward power from the transmitter and radiate it as long as it's matched. If the antenna is not matched to the frequency of the transmitter, the antenna can't radiate all of the power. Its efficiency isn't 100%. So some of that power can't go out in the air, so it's going to get, the only place it has to go is it's going to get reflected back down the cable, back to the transmitter. This can be a problem for a number of reasons. It can create what are called standing waves on the coaxial cable, which increase RFI to adjacent cables, whether they're other RF cables or they're sensor cables. It also, the power that comes back down the cable feeds right back into the transmitter and can heat the transmitter up. And if the reflected power is high enough, it can do damage to the transmitter. And again, not having a perfect match affects the receiver equally as far as poor performance. Next slide. Grounding. Grounding is extremely important for antennas. It's of course important for surge protection of the instrumentation as well, and the solar cells and power supplies and batteries and all of those, but it's equally important within the antenna and also the radio system. It's highly recommended that for every installation that all the key components, including the instrumentation, is grounded, but certainly here both the radios and the power supplies that are sourcing power to the radios, as well as the antennas themselves and the antenna cables, are all protected, all well grounded. And in the case of the antenna cable, a lightning arrestor is used to help mitigate the potential of any kind of high impulse energy that's generated by the lightning to feed back down the antenna cable and damage the radio. Of course, a direct hit to the antenna is never, the surge arrestor is never going to be able to solve that problem. And we've certainly seen a fair share of radios that have been completely burnt to being unrecognizable when lightning hit. But the lightning arrestors are primarily used, and their real focus is if you have a near hit, not a direct hit to the antenna, not even a direct hit to the tower or mast that the antenna are on. But if you have a hit within a half a mile, quarter mile, that can generate very high EMP pulse energy, and that can basically damage a radio. So the surge arrestors are used to, on the coaxial cable side, are used to try to protect the radios from near hits, but not direct hits. Of course, you typically have a much higher probability of a near hit than a direct hit anyway. We tend to recommend a wire gauging size of around 12 gauge for grounding internal components, and 6 gauge for or larger for external equipment, cabinets, antennas, lightning arrestors, what have you, that would be outside of cabinets to have a much heavier ground. All of these grounds need to be fed directly to a ground bus bar and ground rod, daisy chaining from one piece of equipment to the next, to the next, to the next, and then to a ground rod or a really good ground, maybe off of the tower, is not recommended, since you'll get the ground loops in that daisy chain, and you won't get the protection that you're hoping for. Next slide. This is just showing where fully recommend grounding with the lightning arrestor, grounding the radio equipment, and again, in some cases, even more grounds basically tied to the shield of the antenna cable, whether it's up on a tower or just on a mast. If there's a reasonable cable run between the lightning arrestor and the actual antenna, it's recommended that the additional grounding be done along the cable itself. Next slide. Different types of items that can be used, a variety of different lightning arrestors and kits that are available from a variety of RF suppliers for different kinds of lightning arrestors, different ones designed for different frequencies, some designed for external use, some designed just for internal use, and there's numerous kinds available, typically running in the $40, $50, $60 range from some of the suppliers, and readily available to be used. Really no excuse not to use them, even if you operate in a fairly low lightning prone area. It's still money well spent as far as protecting the system and not having it go down due to a near hit of lightning. The other part of that is with whatever kind of grounding is done externally on the cables, there are a variety of sealing kits that can be used to seal the ground wires and the clamps that are on the coaxial cable to keep that nice and dry and clean, so you don't get corrosion over time, and then the grounding connection fails. So variety of items available and readily available to be able to do this. Next slide. Antennas are conductive elements, and they're affected by other conductive elements. Any kind of conductive medium, masts, equipment cabinets, buildings, anything that potentially is conductive will affect the radiation pattern of an antenna. We normally think of an antenna, especially maybe a vertically polarized collinear antenna, as having an equal radiation pattern in all 360 degrees. But if that antenna is up against a tower or up against a mast or up against some sort of rain gauge or what have you, the pattern will change. It will not be omnidirectional. It won't be 360 degrees. So recommendations are that any antenna should be at least one wavelength of its operating frequency away from all other conductive metal items, materials, whatever they are. Of course, this is many times not easy to do. And in some cases, you don't have the option to be able to do this. But these are the recommendations. And here's a short list of just rough numbers as far as what that distance actually is for various frequencies. The higher the frequency, the distance on the wavelength becomes shorter. So at the very high frequencies, it's not as difficult to implement. At the lower frequencies in VHF, in those areas, this is a harder rule to follow. But that's the rule, and these are the distances that that would be nice to plan for and design for if you can, just to maximize the effectiveness of the antenna. Next slide. Thank you. Okay, various tools that can be used to test antennas in the field, starting from very simple tools to more complex tools. And they include just a simple ohm meter. You can do some troubleshooting with an ohm meter, just as far as what some issues are, all the way up to vector network analyzers, which are now field portable. A number of companies make them. And you can do everything you can do in a lab now, you can do in the field, as long as you pay some good money for some of these devices. Next slide. Again, using a simple ohm meter, you can check for cable shorts and opens. You can check continuity of the coaxial cable if you have access to both ends. Sometimes that's difficult, especially if the cable's already been installed. But if it hasn't been installed, it's always a quick check to see, hey, I have this 50 feet of cable that I'm about ready to install. Well, let me do a quick continuity check on both the shield side and also on the center conductor side, just to make sure that everything seems to look good. Once the antenna cable is installed, doing a shorts and open test from one end of the cable, let's say from the transmitter end of the cable, can be problematic because most antennas these days, both the Yagi antennas and the collinear antennas, are specifically designed to have a DC ground between the center conductor of their connector and the shield of their connector to help bleed off any kind of static that might build up on the antenna, as well as, again, being a mitigator of some lightning strikes as well. So typically once the antenna cable is connected to the antenna, a shorts and open test actually fails if done from the transmitting end of the cable. The next option up, thank you. We can go back one. RF power meter. Again, a variety of these meters available. These are good, so you can measure both the forward power we talked about and the reflected power we talked about. These devices put at the transmitter and basically put in line where the lightning arrestor is, or just right out of the transmitter itself, can give you a good indication of what the forward power is that the transmitter is sending, as well as what the reflected power is coming back. And of course, we want maximum forward power and we want 0 for reflected power. If we get something different for reflected power, that's indicating we have a mismatch somewhere. It may be a very low amount of reflected power, and that's typical. In the system, let's say might have 5 or 10 watt transmitter, you may see something in the order of a 1/4 watt or up to a 1/2 watt of reflected power, and that's going to be probably expected. But anything Certainly anything higher than about 10%, 15% reflected power, that's concern for alarm that we have some sort of antenna or antenna cable issue that should be addressed. Next slide. Another device that can be used is it's called a VSWR meter. These are not as common in commercial use. They are used for ham radio operators and others, radio enthusiasts, but effectively they're doing the same thing, measuring forward power and reflected power, and then coming up with what's called the standing wave ratio. Basically the difference between the power going forward and the power being reflected. These can also be useful tools. Again, they provide good use in indicating forward reflected power. Typically, these devices operate at just lower frequencies. And so for any typically above UHF frequencies, typically you would just use a power meter to measure the forward reflected power as opposed to this kind of VSWR meter. Next slide. Kind of moving up the ladder, now we're getting into fairly expensive units. There's a wide range of cost for these, and they're come by all different names, but antenna analyzer is typically what they're referred to as. These are very good devices. They give you very good, accurate readings of many things that are going on as far as the antennas and the antenna cabling. They certainly can measure forward power. They also can measure the antenna impedance. Part of the issue of why are we matched to the right frequency or are we not matched to the right frequency as far as what the antenna's performance is. These devices can measure what's called return loss, which is again looking at power going forward and what's coming back and how good the how good those ratios are at the operating frequency of that you're operating that on the antenna. You can also use a return loss test to sweep an antenna to see where its sweep spot is. And there's questions as far as how well an antenna is performing. You can use the return loss test to see exactly what the antenna is doing as far as the kind of looking from the point of view of the transmitter. So this gives you a real view into from across a big range of frequencies how well the antenna is performing at the frequencies that you need it to perform in. This tool can be used for both installation as well as debugging a problem later on. If you do have some sort of comms problem, these kinds of antenna analyzers can give you a wealth of information as to how well the antenna cable, lightning arrestor, and antenna are performing. Next slide. Then moving up the chain, this is sort of an all-in-one. This has all of the antenna analyzer capabilities, as well as it can also do measure basically distance to a fault as far as a cable is concerned. If there's coaxial cable that has water in it, some sort of water ingress that's happened over time, or if the cable, if it's a longer cable and it's been damaged somehow, you can actually utilize this vector network analyzer in a time domain sense to estimate where a problem can be in a cable. So it can measure forward reflected power, it can do the return loss tests, it can do the impedance matching with Smith chart. You can verify basically quality of the antenna cable itself, and again, it can also do a distance to failure type analysis. These are typically used more in cell sites where you have many RF cables and you have different companies climbing these towers, and antennas tend to get stepped on and smashed and destroyed, and this is probably the best way you can use to figure out where that might be and what you might need to do to repair. So very high-end products. These are not typically used in most city or county type communication sites, but some may have access to these kinds of tools, and if so, then they can be used for debugging a whole host of problems. Next slide. Well, thank you. Again, I apologize for the mishaps of being able to present these slides initially. Sam, I really thank you for jumping in and making that happen. Are there any questions anyone might have as far as any of the details shown here?
Mark, curious, do you need to take any sort of care when securing your coax cables to, say, a mast, or maybe running them through a constrained, or looping it up in a constrained space?
Good point. Yes. First of all, probably twofold answer. Curling coaxial cable, let's say in an installation you have extra cable. It's far better if you can to cut that cable to length and minimize any bends or curls in the cable that are unnecessary. A coil of coaxial cable actually creates some problems in the cable and can change the impedance of the cable and effectively create a mismatch between the transmitter and the antenna. So anytime you can avoid extra runs of cable or cable that you're curling up inside a cabinet or outside up on the antenna mast, far better not to have any coils of the coaxial cable at all. And then the other issue, Tim brought up, it very much so. One thing you do not want to have is the antenna cables basically loose and subject to vibration and movement by the wind. You really want to have these cables lashed down pretty tight all the way along, any type of antenna run or cable run, so that you minimize flexing of the cable, primarily so that the flexing at the cable where the connector is, over time that doesn't start basically failing just due to vibration. So using ample use of cable ties to tie these cables in place. Of course, not so tight that you're crushing the cable, but you still want to obviously maintain the cable to be in the circular form. If it gets crushed and is flat, that can be a real problem. That again changes the impedance of the cable at that point, and that can become a reflection point of the transmit signal and being reflected back to the transmitter, not because it didn't make it to the antenna, but because it got hit basically within the cable itself.
Yeah. Also, I get a question every now and then from clients who about the lightning arrestor. It's not always. Our lightning arrestors are often put in, and they're sort of set and forget until something fails. I was curious if there's any recommended preventative maintenance for lightning arrestors.
Good question. There are different versions of lightning arrestors. Some are basically they only suppress one large surge, and then that's it. And they use typically a small gas discharge tube inside the lightning arrestor. Those lightning arrestors are typically not recommended for use here. There are multi-strike lightning arrestors. Most lightning arrestors produced by Polyphaser and others produce what they call a multi-strike lightning arrestor, and they can take hit after hit after hit. Again, not direct hits, but near hits that basically aren't frying the radio in the process. Certainly, the big issue on a lightning arrestor can't do what it needs to do if it doesn't have a good ground to earth. in a good, very low resistant ground to earth. So we've certainly seen many lightning arresters in enclosures, but unfortunately, there was no separate ground wire tying that lightning arrestor to ground. It was just relying on the shield of the coaxial cable to be a ground, which is not sufficient for any kind of real surge protection.
Thanks, Mark. And I also see in the alert community, particularly with the installation of Alert 2 stations, or in the GOES community, the use of GPS antennas that are active patch antennas. It's my understanding we need to use different arresters for these different types of antennas.
Yes, no, you're right. Basically, with the active GPS antennas, well, let's back up. There are two different types typically of lightning arresters. Some are AC coupled, basically in a 3-path, and some are DC coupled. For most non-GPS antennas, AC coupled lightning arresters work fine. DC lightning arresters are preferred, but they tend to be a bit more expensive. For GPS, if you have an active amplifier at the antenna, you have to use a DC pass lightning arrestor in order to pass the 3 volts or 5 volts or 12 volts that's being fed from the radio, in this case, the GPS receiver, to the GPS antenna. So in that case, yes, special care needs to be taken to make sure that you use a DC passing or DC coupled lightning arrestor to support the power that the active antenna needs to operate.
Right on. Thank you.
Are there any other questions?
Thank you, Mark. I've been watching the questions box and haven't seen any pop up yet, but I will let you know if I see another one in the next minute or so.
Again, Matt, I appreciate the opportunity to present this material and to be able to get that out to many of the users who have participated today within the event.
Yeah, absolutely. I do see a question here for you, Mark.
Yes.
Let's see. Is there a limit to the gain you get by adding more elements to the Yagi antennas?
There is. Just physics and kind of an impure approach. Typically, to get a 3 dB increase in gain, you have to double the number of elements. So if you're already at, let's say, 6 elements, if you want 3D more gain, you have to go to 12 elements. And if you want 3D more gain, then you would have to go to 24 elements. And there is a kind of point of diminishing returns. Typically, once you get to a gain of about 12 dB, that twofold to 3 dB or redoubling in the elements starts falling off to 2 dB of gain for doubling elements down to 1 dB of gain. So there are commercially available some 24 element 2.4 gigahertz antennas, but their gain is only about a dB to a dB and a half more than a 12 element 2.4 gigahertz antenna. So yes, there is a practical limit. It really hits at around 10 to 12 dB of gain on the antenna, which again translates to somewhere between 12 to 16 elements. After that, you're not really seeing any new improvement. You can separately, you can do what's called stacking Yagi antennas. You can put 2 antennas side by side and get increased gain, typically not quite 3 dB, but almost 3 dB. And there are some cases where you can take 12-element Yagi antennas and stack 2 of them with a special, what's called phasing harness, and get additional gain that way. And you get close to 3 dB of gain. But again, once you get that much gain, the beam width of the antenna is so narrow that in practical use, it becomes a little bit hard to point and secure exactly what direction you need to set it up in.
We also have a comment from Ryan D. Clark. He says, nice, informative presentation. Thank you.
Appreciate that. Thank you very much.
Okay, I'm not seeing any other questions, so I think we'll go ahead and wrap up our webinar. Thank you, Mark, and definitely appreciate your time here today. And thank you everyone for tuning in. And we will upload this to our YouTube channel, and we have a webinar coming up in May. I believe it's the last Wednesday in May. I think it's the May 25th, I want to say.
Yeah, that's right.
Okay. All right. Thank you, everyone, and hope you have a good day.
Thank you.
Very good. Thank you.
Thanks, Mark.